This video we're going to look at methods of mathematical proof. A mathematical proof is an argument that establishes that a set of assumptions logically guarantees a particular conclusion. There are many different methods of proof, but two particular methods of interest for us are the methods of direct proof and proof by contradiction. Direct proof states that if statement A is true, it logically follows that statement B must also be true. Proof by contradiction says that statement A and statement B cannot simultaneously be true. So therefore, if we assume that statement A is true, then there's a logical contradiction if statement B is also assumed to be true. Now both these methods are useful, and we'll show this using a particular example. Suppose A is an integer. Then we want to prove the hypothesis that if A squared is even, if and only if A is also even. Now this is actually two separate statements for which we need two different proofs. The first is that when A is even, this implies that A squared is even. For this we'll use the method of direct proof. The second is that A squared is even implies that A is even, and here we'll use the method of contradiction. So let's start with our first proposition. If A is even, then A squared is also even. So if A is even, we can write A equals 2 multiplied by some integer k. If we now square this, we can write A squared equals 4 multiplied by k squared. This is obviously also a multiple of 2, so we can write it as 2 multiplied by 2k squared. And because it's a multiple of 2, it's even. And so, very simply, by the method of direct proof, we've shown that if A is even, then A squared is also even. Now the proof of the second part is a little bit more difficult, as we'll show using the method of contradiction. So the second proposition is that if A squared is even, then A is also even. We're going to start by assuming the opposite, that A is odd, and we're going to show this leads to a logical contradiction. So if A is odd, we can write it as it being equal to k plus 1, where k is an even integer. Now given this, we can write A squared is equal to k plus 1 squared, and expanding that, we can write it as k squared plus 2k plus 1. Now we've already showed that if k is an even number, k squared is even, and 2k is obviously even, so k squared plus 2k is even, and if we add 1 to that, then obviously we're going to get an odd number. So we've shown that if A is odd, then it can only be the case that A squared is also odd. So this is a contradiction. We cannot simultaneously have A squared even and A being odd. So we've now shown both sides of the proposition. We've shown that if A is even, A squared is even. We've now shown that if A squared is even, then it follows that A is also even.